Dr. Bagman, you're rolling. You may proceed.
Okay. Morning, everybody. Remember, we've got homework set number 1 due today. I think I have it right this time. I'll have solutions posted for you this afternoon, so get those. Generic transmission line circuit. A transmission line with known characteristics of length script L with a load ZL at its terminations. We applied Ohm's law, ended up with some useful information defining a reflection coefficient as we see here. Before I go on, also defining some very useful formulas here for the form that the phasor voltage and current take at any particular location on the transmission line, where we find that there's only one unknown constant left in these formulas. Depends on the strength of the source that you apply to the input terminals of the line. But everything else in these equations for phasor voltage and current are known quantities now in terms of the known phase constant and characteristic impedance of the transmission line, and in terms of the known load placed on the transmission line, Z sub L, which appears in the expression for the load reflection coefficient. All right. Then what we did was simply to divide these two expressions to end up with the definition of the impedance on the line, dividing V by I gives you this formula directly. With a little bit of algebra and trig, you can derive this alternative expression for the impedance at any point on the line. And of course, we're not usually interested in the impedance at any particular point. The point that interests us the most is the impedance at the source terminals, at the input of that section of line. That is to say, where x equals minus L. We actually define that as a new symbol, x in. It depends on the length of the line. It is defined as the impedance expression above when x equals minus L, and this is what you get from the formula above, just setting x equal to minus L. We noted last time that in order to use this formula, remember beta L has units of radians. Beta L is itself a useful quantity that we'll be referring to an awful lot in this class. It's called the electrical length of the section of transmission line. It's the meaningful measure of length. It gives us a measure of the length of the line compared to a wavelength. And a line that's electrically short at one frequency might not be electrically short at another frequency. It might be electrically long, because if you change the frequency, you change the wavelength. And at one frequency, a 1 meter long piece of line may be only a thousandth of a wavelength long. That's pretty short electrically. I'd be willing to treat that one using plain old circuit theory. No transmission line theory involved. But at another frequency, that line might be 2 or 3 wavelengths long, in which case I'd say you better turn to the use of transmission lines in trying to analyze that circuit. Well, anyway, we finally left off with taking a look at some special cases of the input impedance for various loads. The first loads that we considered were either, well, match termination, first one. If ZL equals Z0, the formula up above can be very easily seen to give you an input impedance that's always Z0, regardless of the length of the line. Numerator and denominator become identical in that case. The two formulas of special interest to me here are number 2 and 3, though. Either placing a short circuit termination on that length of transmission line or an open circuit termination for the load. And we get these formulas for the input impedance with a short or open circuit termination. Where I noted last time that if you put a short circuit at the end of the sectional line, you don't see a short circuit looking into the input terminals. You see anything but. You see this crazy function of the length of the line, and you change the length of the line, and you'll change what input impedance you do see when you have that short circuit there. But it sure isn't zero, unless, of course, beta L happens to be an integer multiple of pi. At those particular line lengths, you would get the tangent being equal to 0, but normally the tangent function isn't 0. Same thing for the open circuited termination. You're not going to get an open circuit looking into that open circuited section of line. You're going to get this reactive impedance looking into the open circuited line. And that's not an open circuit. Zn isn't infinite, except at those particular locations where the cotangent is infinite, once again where beta L is a multiple of pi. But for any other lengths, the bet's off. Okay, so put an open circuit here, remove the load, and you don't see an open circuit there. Put a short circuit here, short circuit with a piece of wire, you're not going to see a short circuit there. The reason I stress this so much, oops, I'm going backwards. The reason I stress these two facts so much is because, remember when we were talking about the low frequency parameter sets? How were they defined? How would you measure them? You'd take your 2-port device and you'd either open circuit one of the terminals or short circuit one of the terminals. I said that's not a very good thing to do at RF. Well, here's one thing you can see as a reason why that's not necessarily such a great thing to do at RF. Just because you maybe hook a section of wire up to the output terminals and short circuit at the end of that wire, you haven't short circuited the terminals. The terminals will see that input impedance of a section of transmission line. So unless you actually weld those terminals right there at the device together, you're not going to have a short circuit at those terminals. You put any piece of wire of any length whatsoever, no longer a short circuit or an open circuit. All right. Now, I said I'd say a little bit more about these input impedances. Let me turn to the overhead quickly and give you a quick sketch. You'll see this in every book on fields and waves. Let's look at the short circuit case first. Input impedance looks like a tangent function. And I'm just going to do my best to sketch a tangent function here. And so on and so forth for the tangent function. Okay, now Zn is let me not say this. Let's call this X in, where X stands for reactance. And let me say that Z in is JX in. Check out that formula for the input impedance, and you'll see it's pure imaginary. It is inductive in nature here and here and here for those electrical lengths for the transmission line. It's capacitive in nature here and here and here, where X in is negative, giving capacitive reactance. So the input impedance is reactive, it's pure imaginary, but it's either inductive or capacitive, depending on how long the line is. And remember, beta L is just a nice way of writing L divided by the wavelength, L divided by lambda. It's 2 pi times L divided by the wavelength. So change the length of the line, change the reactance you see looking into those input terminals. In a very extreme fashion, the reactance changes like a tangent function. Okay, short circuit. Well, if your line has this particular length or that particular length, yeah, you'll see a short circuit looking into the input terminals. Any other length for your line? No. You're going to see J something. You're going to see an inductive reactance or capacitive reactance. That is the short circuit case, and I can duplicate my artistic effort here. For the open circuit case. For the open circuit case, I've got to sketch, what is it? Minus JZ0 cotan beta L. Minus of a cotangent. Cotangent's 1 over sine. Minus of a cotangent looks like this. Periodic with period pi. And so on and so forth. And we see that for an open circuited section of transmission line, once again, you've got a reactive input impedance looking into those terminals. And the reactance can be inductive in nature, plus J something. It can be capacitive in nature, minus J something. It could even be a zero impedance looking into those lines if they're of the correct length. It could be an open circuit looking into the section of transmission line if they're of other particular lengths. But in general, the best I can say is going to be reactive, and leave it at that. And you have to tell me exactly how long your line is compared to a wavelength for me to be able to tell you anything else. Okay, a couple of other cases that aren't quite as important to us here. You can also pick various particular lengths for the transmission line to end up with nice results coming out of this formula here. Particular lengths where the tangent function does not known things, such as if beta L, the argument of the tangent function, is a multiple of pi. Looking at my graph for the short circuit line, which was a tangent function, I can see the tangent function is always 0 when the argument is a multiple of pi. So if beta L, 2 pi over lambda, times L just happens to be a multiple of pi, then the tangent function goes to 0, and the input impedance is equal to Z0 times ZL over Z0, or in other words, the input impedance is going to be ZL, only when the length is an integer multiple of a half a wavelength, so that 2 pi over lambda times this integer multiple of a half a wavelength gives me n pi for the argument of the tangent function. There's one more I'll look at. Excuse me. If the length of the line is a quarter of a wavelength plus an integer multiple of a half a wavelength, then beta L, the argument of the tangent function, is 2 pi over lambda for beta, lambda over 4 plus n lambda over 2. That gives me pi over 2 plus n pi. And looking at the tangent function, which was my short circuit impedance, looks like the tangent function at pi over 2 plus multiples of pi, that's where the tangent function goes to infinity. That's its asymptotes. The tangent function goes to infinity. So that's the particular lengths where the tangent function in numerator and denominator get really, really big, and they swamp out those two terms in the numerator and denominator, leaving us, for all practical purposes, just get rid of those terms, leaving us with Z0 times Z0 over ZL. You can then cancel the tangent functions. So overall, the input impedance becomes Z0 squared over ZL. This is a useful fact when designing certain types of transmission line circuits. This thing is called, when you have a line that's of length a quarter of a wavelength plus an integer multiple of a half wavelength, it's called an impedance inverter. The reason that it's called an impedance inverter is because the input impedance varies inversely with the load impedance. Has to do with 1 over ZL. The input impedance is inversely proportional to the load impedance. And for some particular crazy types of transmission line circuits, it's useful to be able to have a section of line that would give us this type of behavior, 1 over the load impedance. We won't need that so much for this class. One more picture that you often seen drawn in textbooks dealing with transmission lines is this familiar picture of standing wave patterns set up on transmission lines. Whenever you have forward traveling waves and backward traveling waves existing in the same medium, you're going to set up standing waves. In this case, we've got forward traveling voltage waves and backward traveling voltage waves on our transmission line, and forward and backward current waves on the transmission line. It should come as no surprise that you're going to have standing wave patterns for the voltage and the current on the transmission line. And here's a sketch of this type of standing wave pattern that you see on a transmission line. And if you do this in the laboratory, take a section of line and connect it up to a source on one end and a load on the other end that's not matched, so you get some reflection. So you have these forward and backward voltage waves, let's say, on the line. And you take a probe, like a voltmeter lead, and measure the magnitude of the voltage at various locations on the line. This is what you'll measure once you graph it out. As you change position on that line, you'll see voltage minima and voltage maxima occurring. This is a standard experiment in Lab 2. Interestingly, the distance between adjacent maxima or adjacent minima on this standing wave pattern is lambda over 2, half a wavelength, not a full wavelength. You can use this, by the way, to measure the wavelength experimentally. And this is what we do in Lab 2. We have the students measure the wavelength by finding where their probe on the voltmeter measures the minimum, and then moving up the line and finding where the probe measures the next minimum and measuring that distance, and then saying that's half a wavelength. And by the way, we have the measure minima, not maxima, on these curves. The reason for that is because, like it's shown here, the minima are sharper than the maxima. So it's easier to find a null. It's a sharper measurement than finding this broader maximum. Anyway, let me denote the maximum possible value of voltage on this standing wave pattern as Vmax, and the minimum value as Vmin. Then, often done thing is to define a standing wave ratio. A standing wave ratio defined as Vmax over Vmin. And you can show that the standing wave ratio is related to the load reflection coefficient in this way. And this standing wave ratio is a useful quantity. It tells you basically how much of a standing wave pattern you have on the transmission line. The standing wave ratio is also Vmax over Vmin. If the standing wave ratio is equal to 1, that means that Vmax and Vmin are equal to one another. And I guess this pattern would be just a straight line. The minima are equal to the maxima. There really is no standing wave there. So the minimum value of the standing wave ratio is equal to 1. By the way, what load would I put on the transmission line to have a standing wave ratio of 1? Yeah, that's the best case. That's the matched load. A matched load would give you what for the reflection coefficient? 0 reflection when you have a matched load. 0 reflection coefficient. What does this formula say? Standing wave ratio would be 1 plus 0 over 1 minus 0. Yeah, it would be 1. Standing wave ratio 1. That's perfect match. The worst possible case is standing wave ratio which is infinite. How would you get a standing wave ratio of infinity? Well, you can see here that if the denominator went to 0, that is to say, if the magnitude of the reflection coefficient was 1, then you'd have 0 in the denominator here. Yeah, you could mathematically get a standing wave ratio that would be infinite. What does that mean on the drawing up here? Remember, the standing wave ratio is Vmax over Vmin. That's another way of writing it. Vmax over Vmin infinite? What would Vmin be then? Well, once again, if Vmin was 0, then Vmax over Vmin would be infinite. That means in this standing wave pattern, those minima would go all the way down to 0. Okay? Now, I say that the standing wave ratio is Vmax over Vmin. And I also say that the standing wave ratio is this quantity over that quantity. You can see that because Vmax is given by this formula. Vmin is given by that formula, and dividing those two right-hand sides by one another gives me the formula I have written there. All right, well, let's see if I can justify why I say the maximum possible voltage is this given by this formula, and the minimum possible voltage is given by that formula. Where to start? Well, let's go back to the formula for voltage. There it is. I need to use this formula and find out when it's maximum and when it's minimum. Now, remember, on the line, that is to say, as x changes, you change whether you're at the location of a maximum or at the location of a minimum. So let's let x be a variable and let x vary and find out what the maximum value of v of x is going to be as we let x change. So we start with this. There's my forward traveling wave. Here's the reflection coefficient times the backward traveling wave term. Okay. I'm going to wave my hands a bit, make some drawings, and try to convince you of the pair of formulas that I have written in the notes. Let's, for a moment, forget about that term. The constant multiplier out in front of the voltage, because that's going to be the same constant multiplier in front of v of x, whether we're looking for the maximum or the minimum. And we're going to take the ratio of the two to find the standing wave ratio. So that v0 plus really doesn't make a whole lot of difference. Let me draw the first term. That is what e to the minus j beta x looks like in the complex plane. It is represented in the complex plane as a vector from the origin to a point in the complex plane. It's easiest to describe that vector in the complex plane in polar coordinates, that is, in terms of its length and its angle. In terms of that angle and in terms of that length. What's the length of that arrow there representing e to the minus j beta x? It's 1. It's the magnitude of e to the j beta x. But e to the j anything has length of 1. It's cosine plus j sine, and the length is the square root of the sum of the squares of the real part and the imaginary part. Cosine squared plus sine squared is 1. We all know that e to the j x points in the complex plane in some direction, but it always has length 1. How about that angle? What's that angle equal to? Yeah. Let me call it minus beta x, saying that I'm measuring angles positive. Yeah, I shouldn't be minus beta x the way I have it drawn. It would be, now, let's call it minus beta x. I don't want to confuse the issue. That angle is minus beta x, where beta x is some value, 30 degrees or something like that. So it's 1 at an angle of minus 30 degrees, let's say, for e to the minus j beta x. And as you change locations in the complex plane, what happens? Well, the tip of that vector is going to describe a circle. It's going to rotate as I move around along the transmission line. And I'm just looking at it at some particular location. Now, that's that term. How about this term? What does that guy look like? I can draw that as a vector in the complex plane. And I can add those two complex numbers together by taking the first complex number as a vector and then putting the tail of the second complex number as a vector up to the tip of the first one, and then drawing the vector result of adding those two vectors together. Okay, so what I'm saying is I'm going to make a little coordinate system right here, and at that location I'm going to sketch in the second term, starting at that point, and add the results. What is that second term going to look like? Well, I'm not sure. Let me draw it like this and say that that thing is my gamma e to the plus j beta x term. And when I add those two together, where's my red pen? Here we go. Let's add some neat special effects here. That is the sum. That's in brackets up above. Okay, now, first of all, I drew that second vector smaller than the first one. Why is that? Because you can show that the voltage reflection coefficient has a magnitude less than or equal to 1. You will show on homework set number 2. That's one of the problems. And by the way, homework set 2, I posted it this morning, due a week from today. The voltage reflection coefficient always has a magnitude less than 1. So that's why I drew that vector as being smaller than the other one. The other thing is, what's this angle here? You might jump to the hasty conclusion that that angle is plus beta x. Well, close. That angle is plus beta x, sure enough, but you may have to add some more on to that, because gamma in general is a complex reflection coefficient. It's in general a complex number. So there might be a phase angle associated with gamma. So that angle may be the angle of beta x, the angle beta x, plus a little more, or minus a little more. I don't know, depending on exactly what the reflection coefficient is. All right, now, there's the picture. Oh, by the way, what happens as you move up and down the transmission line to that term? Well, that one does its own little bit, rotating around in a circle about the tip of the other one. Think of it this way. Think of this as being a stick connecting the origin to this point right here of length 1. And that stick is free to rotate about the origin. Then you take another stick, a little bit shorter than the first one, you connect it up to the end of the first stick, and allow that stick to rotate around the end of the first stick. Then you take a rubber band, and you stretch that rubber band from the origin to the tip of the second stick. Now, how big is that sum in brackets there? It's the length of that rubber band. But now remember, the first stick can rotate around the origin, and the second stick can rotate around the tip of the first stick. As you move up and down the line, that's exactly what happens. Those angles change. And I can't tell you exactly what those angles are unless you tell me exactly where you are on the line. Here's one thing I know, though. The longest that rubber band is ever going to stretch is what? 1 plus the length of the second stick, because the first stick is length 1, and the second stick has a length that's equal to the length of the magnitude of the reflection coefficient. That's my maximum for the rubber band. And what's the minimum? 1 minus, right? If that second stick pointed in exactly the opposite direction. That's where I'm going to get the minimum possible value for the length of the rubber band being stretched. Okay. Now, remember, these angles all change. They rotate around as x changes, as you move up and down the line. But somewhere on that line, they're going to line up, those two sticks. And at other locations on the line, they're going to be in opposite directions. In between, well, the resultant vector would have in-between lengths. Okay, well, that's how, I hope, I can argue that the maximum possible value for the voltage on the line is where those two sticks line up. The minimum possible value is where they're in opposite directions. And by the way, remember that V0 that I said we could ignore? We can ignore it once we divide Vmax by Vmin to end up with that formula. That diagram there, by the way, has a name. That's called a crank diagram. So if you ever hear someone talking about a crank diagram, that's what they're talking about there. Okay, enough said about transmission lines for the time being. Let's talk about the scattering matrix, the S parameters. And by the way, I'm going to introduce the chain parameters at the same time. They're like the chain parameters for low-frequency circuits, ABCD type parameters. All right, now, I've already talked about this a lot. At RF, open circuits, short circuits, that's a no-no. We're going to introduce a parameter set, the S parameters, that's based on incident and reflected waves, no longer just voltages and currents. We're going to be talking waves now. And these S parameters have the one big advantage that they don't depend on open circuit and short circuit measurements. Okay. Defined in terms of waves. Well, we've already seen that when you're working with transmission lines, electrically large circuits, voltages and currents consist of waves. There are forward traveling wave parts and backward traveling wave parts. I break up the total voltage on the line into its forward traveling wave term and into its backward traveling wave term. And I do the same thing for the currents, where, remember, the backward traveling wave current actually subtracts from the forward traveling wave current. Not the same case as what we had with the voltages. This is just disguised notation for what we've seen already. Here's what I mean by V plus and V minus. And here's what I mean by I plus and I minus. I just took these formulas right here and wrote that term and called it V plus, and then took that term and called it V minus. I took this term and called it I plus, and I took that term and called it I minus. That's all I've done here. Disguised those two formulas in that way. So those are identical to the two formulas we had previously for V and I. There's our reflection coefficient at general locations on the line, backward voltage divided by forward voltage. Here's the load reflection coefficient. The same thing, only now at the load terminals. Okay, now we get down to the actual definitions. We're going to be working a lot this semester with A of x and B of x, small a and small b. A of x is the forward traveling wave, and B of x is the backward traveling wave. I define, this is definition now, I define the forward traveling wave to be equal to the forward traveling voltage wave divided by this kind of strange normalization, divided by the square root of Z0, where Z0 is the characteristic impedance of the transmission line, 50 usually. So take the forward traveling voltage wave and divide by square root of 50. That's what I mean by A. B, take the backward traveling wave and divide by the square root of the characteristic impedance. That's all I mean by the backward traveling wave. The units on these things aren't too nice. Voltage, of course, has units of volts. Square root of impedance, all I can say there is the units there is square root of impedance. So volts divided by square root of impedance. Same thing for B. Kind of strange units. But don't worry about the units. We'll see the interesting units come out in a few more minutes. Well, since the reflection coefficient was V minus over V plus, I could solve this equation for V minus in terms of B, solve that equation for V plus in terms of A, and end up with saying reflection coefficient is just B divided by A also. Or B is equal to reflection coefficient times A. Now, here's the answer to a question that's probably on a lot of your minds at this point. What's the relationship between voltage and current and these waves, A and B? I'm not talking forward traveling voltage or backward traveling voltage or forward and backward current. What happens if I just go into the lab and measure the voltage with a voltmeter or measure the current with the ammeter? Well, what you're measuring there is total voltage and total current. You're measuring the sum of the forward and backward voltages. You're measuring the difference, actually, of the forward and backward currents. And so it'd be nice to have a set of formulas that would allow us to go from those straightforward laboratory measurements of voltage and current to the waves A and B, and vice versa. Well, here they are. You tell me what your lab measurements were for voltage and current, and I'll tell you what A was. I'll just put those two measurements together in this way to get A. And I can also tell you what B is. I'll put the two measurements together there in this way to find out what B was. So if you give your fancy RF circuit to a technician, and that technician's more comfortable with measuring voltages and currents using a straightforward ammeter and voltmeter, let him do it. And then when you get those measurements back, if you want to do RF stuff in terms of waves, just take those measurements and combine them the way I have shown here. Similarly, of course, you can invert those formulas and end up with simple formulas for total voltage and total current in terms of the waves A and B by combining them in this way. Okay. You'll show this. I say it's easy to show. You'll show it on the next homework assignment. It's one of the problems. Okay. Now, here's our two-port back again. But now we're talking about waves at each port. I'm going to call the A waves the incident waves. A means incident wave. A means wave traveling into a port. So if I call this port 1 and that port 2, I automatically know what I'm talking about when I say A1 and A2. A1 points into port 1 and A2 is the wave going into port 2. Similarly, the B's, those are what I'm going to call the reflected waves or outward going waves. I usually use the word reflected waves. B1 comes out of port 1 and B2 comes out of port 2. Now, I'm going to be considering only linear two ports. So it should come as no surprise that I'm going to write linear equations relating my waves together. And here are the linear equations. I'm going to solve for the reflected waves, B1 and B2, in terms of the incident waves. And there's the two most general linear equations that I can write to relate the A's and the B's together in terms of constant coefficients, S11, S12, S21, and S22, which are the scattering parameters of the two-port network. In matrix notation, I get this. B1 vector equals the scattering matrix times the A vector. So there I've defined the scattering parameters. I've defined scattering matrix in terms of these incident and reflected waves on the two-port. Now, excuse me, how would I compute or measure scattering parameters? Okay, looking at this equation, let's say that I wanted to find S11. I could find S11 in much the same way we were talking about with the low-frequency circuits. I could find S11 if I could just get rid of that term. That is to say, if I could just make sure A2 was equal to 0. If A2 is equal to 0, that term would be gone, and S11 would be nothing more than B1 divided by A1. And I'm assuming those A's and B's are things we could measure in the laboratory. And similarly for the other scattering parameters. We could find them all if we only had some easy way to make sure that either A1 was equal to 0 or A2 was equal to 0 in the appropriate equations at the appropriate times, or in the laboratory making the appropriate measurements. A1, A2, those are the incident waves. All right, now remember when we were doing the low frequency circuits, what we did was tricks like this. We would short circuit or open circuit the other port to make sure either the voltage there or the current there was equal to 0. Now you can't short circuit or open circuit these ports to make sure that, let's say, A2 was equal to 0. A1, well, I guess I could produce an A1, a wave incident on the two-port, by hooking some sort of a source up to port 1. And we want to make sure A2 is equal to 0 in order to be able to measure S11 or calculate S11. A2 is the wave incident from port 2. You might say to yourself, oh, that's easy. Just make sure you don't hook a source up to port 2, and then there will be no wave incident on port 2. No, unfortunately, not the case. Imagine putting a load here on port 2. This can be thought of as a transmission line connecting a two-port network up to a load now. What happens if you have a wave traveling down the transmission line incident on a load over here? If that load's not a matched load, part of that wave is going to be reflected back off of the load. In other words, if the load's not matched to the transmission line over here, a wave that gets out into port 2 can be reflected back into port 2, even though there's no source over there. Matched, that's the key. If I match terminated port 2, then even if there's some wave that does make it through the 2-port due to a source connected up to port 1, that wave coming out of port 2, it would strike that matched load on port 2. All of it would be absorbed. There would be no reflected wave. That's what we mean by a matched termination. A2 would be equal to 0. Bingo. That's how you measure the scattering parameters. They're not open circuit parameters. They're not short circuit parameters. They're match termination parameters. They're parameters that you measure using match terminations. Okay, well, here's the equation corresponding to finding S11. If you can set A2 equal to 0, then S11 is nothing more than B1 divided by A1. Also, if A2 is equal to 0, you could solve the second equation for B2 in terms of A1, or then solve for S21 as B2 divided by A1, as long as that second term went away in the second equation. If you make the first term in the first equation go away, then you can solve for S12. It's just B1 divided by A2. Making the first term go away in the second equation means you can solve for S22 as B2 divided by A2. Everybody comfortable with that now that they've seen the low frequency parameters again? Okay, and these things actually have names associated with them. S11 is often called the input reflection coefficient of the 2-port when port 2 is matched. When port 2 is matched. That's important. Matching port 2 means A2 will be equal to 0. Then, measure what comes out of port 1 when you have something incident on port 1. That's reflection. That's an incident wave being reflected off of port 1. That's why we call S11 a reflection coefficient when port 2 is matched. Same thing holds for the dual case. And you'll hear me say this word dual a lot. The dual case means substitute port 1 for port 2. Do it at the other port now. Here, that's the one I want to talk about. The other reflection coefficient. Match port 2. Put a source up to port 1. Figure out how much gets reflected out of match port 1. Put a source on port 2. Figure out how much gets reflected out of port 2 when you got that source hooked up to port 2. Take the ratio of the reflected wave to the incident wave on port 2 when port 1 is matched. That's the output reflection coefficient when port 1 is matched, S22. The other two coefficients have to do with transmission of signals through the 2-port network. S21 is by far the most interesting one. S21 is known as the forward transmission coefficient when port 2 is matched. And here's the picture you should have of S21. S21 tells you B2 when you have an A1. That is to say, it tells you how much comes out of port 2 when you have a source hooked up to port 1. By the way, match port 2. Put a matched load over there on port 2. And then figure out how much of that wave strikes that matched load on port 2. Forward transmission coefficient. We're going to be talking about this forward transmission coefficient a lot in this class, because the 2-port that we're going to be most concerned with here is an amplifier. And the key thing for an amplifier is its amplification. How much comes out of the output of the amp when you've got a signal coming in? Yeah?
Do you mind just showing mathematically how when you have a match, for example, for the forward transmission coefficient,
Mm-hmm.
just to get to the S21, see what I'm saying? Like just show the calculations, what does it mean to match and get to that final equation?
Yes, we're going to talk about that. It's actually right there. This is the circuit that you would use to measure S11. I'll get to that in just a second. So that's the forward transmission coefficient. It's basically the gain of the amplifier, S21. S12, that's the reverse transmission coefficient. It talks about what comes out of port 1 when you have something hooked up to port 2. By the way, port 1 has to be match terminated in order for this parameter to make sense. And I guess from the amplifier point of view, it's talking about backward amplification. You know, what would you get out of the input terminals of the amp if you hooked up a source to the output terminals of the amp? Okay, now let's get to that question. How would you, let's say, measure one of these coefficients in the laboratory? Here's what I would do to measure S11. S11 requires port 2 to be matched. So if you've got a characteristic impedance of Z0 for the transmission line hooked up to port 2, place a load on port 2 that's match terminated load. That is to say, has the same characteristic, has the same impedance as the characteristic impedance. If it's a 50 ohm line, put a 50 ohm source there on port 2. Now, place a source on port 1 and measure the incident wave, which is basically saying measure the forward traveling voltage wave at port 1. Calculate what it is based on what source you're putting in there. Then measure the reflected wave off of port 1. Measure how much wave gets reflected there. Take the ratio of the two, and that's what we mean by S11. By the way, just because you have a matched load here doesn't mean there's nothing that gets through that 2-port. You hook a source up to port 1, and this 2-port could even be an amplifier. B2 could be a huge signal coming out the other end of that amp. But you got a 50 ohm load there. All that huge signal coming out of the other end of the amp is going to be absorbed. None of it's going to be reflected back up into the output of the amplifier. So A2 is indeed equal to 0. So this is the same setup, by the way, I would use in the lab to measure S21. S21 also requires A2 to be equal to 0, and that's the setup that you'd use, a matched load at port 2, to make sure A2 is equal to 0. Only now the measurement to perform for S21 would be, connect a source up to the input terminals of the amp, but now measure what comes out of the amp, B2, and take the ratio of those two. If it's a good amp, you're going to end up with a good gain there. B2 is going to be big compared to A1. S21 will be a large number.
Is that why your speakers have to match like your power amplifier?
Have you ever heard of speakers matching the amp? Yeah, absolutely. Have you ever heard of, what's the common, 25 ohm speakers? 5 ohm speakers? 8 ohm. 8 ohm. There we go. I couldn't come up with that for some reason. 8 ohm speakers. Yeah, they always talk about 8 ohm speakers. That's what they're talking about. They're talking about that speaker matching the output impedance of the amplifier for maximum power transfer, so that power comes out of that amp but doesn't get reflected back in. Absolutely. Here's a picture I keep in my mind. And by another couple of weeks, once you start working with these scattering parameters, this picture is going to make a lot more sense to you. It's just sort of a schematic way that I remember what the different scattering parameters represent. Actually, this picture is a fairly common one, even on some measurement equipment that's used in the laboratory to measure scattering parameters. They sometimes even paste that picture to the equipment, just so you know what it is that you're measuring. So here we got a general 2-port network, and here you got some wave coming in and some wave being reflected out of port 1, some wave going into port 2, and some wave coming out of port 2. Here is the general flow of signals through the two-port network. In general, how would you figure out, in a general two-port network, how big a signal would be coming out of port 2? Well, I can think of two ways to have a signal come out of port 2. One thing that could happen that would produce a signal coming out of port 2 is I could put a signal into port 1. And maybe that thing is an amplifier. And maybe it amplifies with this forward transmission coefficient, S21, to produce an amplified signal coming out of port 2. Right, that's a good way to get a B2 coming out of the other side. But that's not the only way. What happens if we also had a signal coming into port 2? For some reason or other, there was some sort of a source or something over here that caused the signal to come into port 2. Now, there's a reflection coefficient known as the output reflection coefficient when the input is matched. That's S22. What does S22 tell us? S22 basically tells us how much of a signal that goes into port 2 would just be reflected right back off of port 2 and come out of port 2 again. Wouldn't even make it into the two-port network. It's reflected right off of the output terminals. This can happen. So B2 in general consists of two parts. It consists of an amplified version of the signal into port 1 plus possibly a reflected portion of some signal that could be input into port 2. And by the way, that's exactly what we have here as an equation for B2. B2 is equal to some coefficient times whatever we put into port 1, but also could be some reflection taking place, making a signal that comes into A2 just come right out as a B2, reflected right off of those output ports. So that's what that curvy arrow there is supposed to represent. It tells you what the function of S22 is. S22 talks about how much of a signal going into port 2 would just be reflected right back out without making it into the two-port. S11 has the same interpretation. Just because you have a huge source hooked up over here to your two-port network doesn't mean that the entire signal that your source puts out is going to make it into the two-port network. Some of that signal could be reflected right off of the input terminals and never make it into the two-port. S11 gives us an indication of how much of that signal just gets reflected off of port 1 without making it into the two-port. Finally, S12, that's that reverse transmission coefficient we were talking about. If you have a signal coming into port 2, some of that could possibly pass through your amplifier in the opposite direction and make it from the output terminals of the amplifier to the input terminals of the amplifier and contribute to B1. So what would B1 be in general? B1 would be, a portion of it would be a reflected part of A1, S11 times A1, plus the possibility of part of A2 passing through in the opposite direction, given by S12 times A2. And that's the second equation in our pair of linear equations for the two-port network. Okay, so that's just a drawing that I use to help me remember the meaning of the different scattering parameters. All right, now we can define chain parameters for the two-port, sometimes called transfer parameters or T parameters for the two-port, in much the same way that we did for low-frequency two-ports, where instead of B1 and B2 solved in terms of A1 and A2, we use instead A1 and B1. both A and B at port 1 solved for in terms of A and B at port 2. This is the same way, basically, that we define the ABCD parameters in terms of voltage and current at one of the ports in terms of voltage and current at the other port. Now we're talking about waves, A and B, at one port in terms of the other port. And you can define the constant coefficients in that set of linear relations as the T parameters and come up with a T parameter matrix. And the T parameters are very simply related to the scattering parameters. And you can find conversion formulas for them in the textbook as well. And the T parameters are useful for RF 2 ports, just like the ABCD parameters are useful at low frequencies in the case that you've got a cascaded pair of 2 ports. Because then the overall T parameters for the cascaded pair is equal to the matrix product of the T parameter matrices of the individual 2 ports. So if you wanted to find the T parameters for the overall cascaded pair, it's just the product of the matrices for the individual 2 ports. Enough said. Well suited for computers. Now, I'm going to go quickly through this one, too. In the laboratory, this can become important, but it's not quite as important to us in this class. But I mention it simply because it is something that is done in the laboratory when measuring scattering parameters. Let's say that we have an RF circuit board, and somewhere on that RF circuit board is appropriately enough for our class an RF amplifier, and we wanted to measure the scattering parameters of the RF amplifier. Okay, there's a device called a network analyzer. Looks kind of like a fancy oscilloscope. It's got a couple of leads. Well, actually, it's got several leads that you hook up to a device, an RF device, and it'll measure the scattering parameters for you. So I want to take my network analyzer and hook it up to this circuit board and measure the scattering parameters of the RF amp. However, that RF amp usually is connected up to connectors at the edge of the board. Using pieces of transmission line. So here's the connector on one edge of the board, and here's the connector over on the other edge of the board. Let's say that that transmission line had length L1 and that transmission line had length L2, not necessarily equal to one another. And we take the leads of the network analyzer and hook it up to the connector on one end of the board and the leads on the other end of the network analyzer to the other end of the board. And you measure the scattering parameters using the network analyzer and come up with S11, S12, S21, and S22. That's what the network analyzer is built for. Have we found the scattering parameters of the amp Unfortunately, the answer is no. We've found the scattering parameters using that setup of the amp plus an input transmission line of length L1 and an output transmission line of length L2. That's what you've measured. What you'd like to do is to what's called de-embed the S parameters of the actual amplifier itself from the measured scattering parameters. What you've measured are the scattering parameters of the circuit. That includes the amplifier, sure enough, but it also includes a couple lengths of transmission line. Okay, well, that's the setup in the lab. Here's the answer to how you de-embed. I'm not going to go through the details. You'll see them done in the textbook. If you call the scattering parameters of the amp S, and if you call the scattering parameters of the embedded amplifier, the amp plus transmission lines, S primes, S11 prime, S12 prime, etc., then here's the relationship right there. Here's the relationship of the embedded parameters in terms of the scattering parameters of the actual amplifier. This isn't the equation that's most important. There's the equation that's usually used in practice, is to get the scattering parameter of the amplifier in terms of the scattering parameters that you measured for the amp plus transmission lines. The only difference being is those scattering parameters have extra phase terms added into them that you've got to get rid of. Phase terms due to the fact that the signals coming out of the amp travel down the transmission lines from each side, picking up phase delay as they travel. So you simply get rid of those added phase terms by multiplying by appropriate factors, and here they are. In terms of L1 and L2, the length of the two lines connected up to the terminals of the amp, and beta, the phase constant, 2 pi over lambda for the transmission lines. Okay, now let's talk a little bit about the scattering parameters themselves. And I'm going to go through some pretty messy looking equations, but I'm going to do it briefly. I'm not going to go through all of the details. You'll find the details here in the notes, and you'll find even further details in the textbook. So I encourage you to look at this section of the textbook. Here's another embedded problem. Here's a two-port network with its scattering parameters, S. And I connect up a transmission line of length L1 to one side, to port 1, and connect up a transmission line of length L2 to port 2. Then I can talk about V1 and I1 on the line connected to port 1. V2 and I2 connected on the line connected to port 2. And, oops, I didn't mean to do that. Let me go back. Too far. Where am I? Here's where I want it to be. Here are the formulas for V and I, and the formulas for A and B. These are the same formulas we just got done looking at. Don't let those formulas scare you. They're just formulas for V and I and corresponding formulas for A and B at either port. I is equal to 1 or 2 here. So even write that down. I equals 1 or 2. That's all I mean by I. I'm writing down the formulas relating V and I and A and B twice here, but I'm saving myself some effort by using the subscript I. These are nothing but the formulas we saw previously relating normalized waves and voltages and currents. They're these formulas, okay? Or I said it's easy to show that, and I said you're going to show it in the homework. It's these formulas. I just saved myself some effort by writing them in general form for both ports at the same time. Okay, now, here is a very useful and interesting characterization of the waves A and B. And that is, A and B are real convenient to use when you want to do calculations of power for RF circuits. Because you can talk about incident power and reflected power at both ports. I, once again, I is just 1 or 2, depending on which of those 2 ports I'm talking about. And if you connect a source up to one of those ports, that source will produce power. That power is incident on the port of the 2-port network. But also, some of that power might make it into the 2-port network, but some of it may be reflected back off of the 2-port network. And so it's interesting to be able to talk about incident power and reflected power. And to do that, I talk about incident voltages and currents or reflected voltages and currents. Let me say it this way. Voltages and currents traveling in the plus x direction and voltages and currents traveling in the minus x direction to define incident power and reflected power. This is the usual way of doing it in circuit theory, using phasors. 1/2 real part VI conjugate. Right? Everybody remember that? 1/2. Where does the 1/2 come in? Why 1/2? You all remember that, right? 1/2 VI conjugate. Why 1/2? Because we're using peak values. I'm not using RMS here. We're always talking about peak values. And these are sinusoidally varying quantities, actually. And when you average over one period of time, that's where that factor of 1/2 comes in. That's because cosine squared is equal to 1/2 of 1 plus cosine 2x. And when you average that over one period, the cosine goes away, but the 1/2 don't. That's where the 1/2 comes in. Okay, circuit stuff. All right, but of course, I is equal to V divided by Z, where we use Z0 because we have either forward waves or backward waves, and we know that the ratio is the characteristic impedance. And I'm going to assume, just for simplicity here, that we're dealing with a lossless line, which we normally do in this class. So Z0 is a real quantity, let's say 50 ohms, so we don't have to worry about conjugating it or worrying about the real part there. And all we have is VI magnitude squared, VI times VI conjugate, which is real, and we take the real part of that. That's just the magnitude squared. Well, nicely enough, A, incident wave, was defined as V plus divided by square root of Z0. What I've got here is V plus squared divided by Z0. I've got A times A, combining those two terms. In other words, I have magnitude of A squared. Can't do anything about the 1/2. It's still there. Incident power, then, can be written as magnitude of the incident wave squared divided by 2. 1/2 magnitude of incident wave squared. Okay? Same thing for reflected power. Reflected power, well, sure enough, just as you'd guess, is related to the reflected wave, and it's easily enough given by magnitude of reflected wave squared divided by 2. Some people even call A and B normalized incident and reflected power waves. I don't like that notation. I think next time I type out these notes, I'm going to take that out altogether. I think that's more confusing than helpful. Okay, now comes the circuit theory. The original circuit, you remember that one? It's this thing here. We're going to do a little circuit theory on that one. At the load, V2 is Z times I, where we're putting a matched load up to the load. So we have A2 equal to 0 because of the matched load condition. V1, the voltage that you get appearing at the terminals of the two-port, there's a two-port network hooked in here in the original circuit, is not the source voltage. I'm connecting up a Thevenin equivalent source on one side. The Thevenin equivalent source has an internal impedance associated with it. So it's an ideal voltage source plus the Thevenin equivalent impedance of the source. And I'm saying that we're going to use a 50 ohm source. It's a matched source. Then the voltage that appears across the terminals of the source isn't just the ideal voltage source voltage, but it actually is V minus Z0 times whatever current happens to be running through the internal or Thevenin equivalent impedance. Then A1 can be written in the usual way as voltage plus Z0 times the current. That's from the previous column. But here's the voltage, here's the current. Those two terms cancel out, giving me just this expression for the incident wave produced by that Thevenin equivalent voltage source in terms of its voltage and divided by 2 times the square root of Z0. This is interesting because it tells us that the voltage applied to the line by the source is actually E divided by 2, because E is divided between the internal impedance of the source and the line impedance of Z0. So you've got 2 series impedances, and we're interested in the voltage on the line, which is only 1/2 of the total voltage. Incident power, well, that's, as we just saw, 1/2 of magnitude A1 squared. Use this for A1, so there it is. Incident power supplied by our Thevenin equivalent source is magnitude E1 squared divided by 8Z0. 8Z0. This is an important quantity. It's known as the power available from the source, and it even has its own symbol. We'll see more of this later on. It's called PAVS, available from the source. It is defined as the incident power. It's defined as 1/2 A1 squared, and it's equal to that for a matched source. Where does the 8 come from once again? The 8 comes from 2 different places. First, power is 1/2 of A1 magnitude squared. Because remember, we're dealing with peak quantities here, that 1/2 has to do with time averaging sinusoids. The other factor of 4 that's left over comes from here. Comes from the fact that the voltage that actually appears on the transmission line here is not E1. It's E1 divided by 2 because we've got a voltage division happening. We've got the internal impedance of the Thevenin source, and we've got the transmission line of characteristic impedance Z0 connected here. And we're wondering what V1 is. Well, it's E1 times the voltage division factor of Z0 over Z0 plus Z0, or half. Let's see if I can find out where I'm at again. Oh, I'm losing my place. This isn't fun, I'm sorry. There I am, finally. Okay, that's where the 8 came from. 1/2 time average, and 1/2 from voltage division for the Thevenin source squared. Okay. How about the reflected power? Not all that available power makes it into the 2-port. Part of it can be reflected. And what part is reflected? Well, we've already talked about that. 1/2 of B1 magnitude squared. And you can find that easily enough by taking the difference between the total power and the incident power. So basically all I'm saying here is reflected power is total power minus incident power. And doing a few calculations of a similar nature on port 2 will allow calculations of things like the wave that makes it out of port 2 in terms of current, and the power delivered to the load, which is the power at port 2, once again, unsurprisingly, in terms of the square of the outgoing wave or reflected wave, B2, at port 2, with that factor of 1/2. All right. Unfortunately, we're running out of time. Rather than trying to get into this section, why don't we call it quits here for the day? This section includes an example that I'm going to work. The example is posted on Blackboard. So make sure you check out the examples folder and download that example, which I will get into next time. And that will pretty much end our look at Chapter 1 notes. So by next time, we'll also be looking at the Chapter 2 notes, diving into the material on Smith charts. Also, as I said at the beginning of lecture, homework assignment 2 is posted, due a week from today. It includes a couple of those easy exercises that I pointed out from the notes today. Also includes a Smith chart problem. So get hold of those Smith charts, download some from Blackboard, get hold of a compass and a straight edge to allow you to work on the homework assignment 2 due a week from today. Any questions before we call it a day? All right.